Okay, we're going to go ahead and do this final part of 2.3. It's just this one problem, but this helps you relate it to things that come from science or even engineering. In this case, would be like electrical engineering, but or something you would even do in physics. So here we have Ohm's law for electrical circuits. Basically, it works for any what are called ohmic devices, which in this case will be a resistor, so that'll be just fine. Like the one shown in the figure, states that V equals Ri. So that's voltage equals resistance times current. If you're curious, voltage you can think of as your potential to move a charge. So it's not necessarily how much charge you are moving, it's just how much charge you could move if it was available. Kind of like if you say, I could lift 100 pounds, that doesn't mean you necessarily are lifting 100 pounds right now, but you could if it was available. And so the idea here is, if it's available, you could move you could move that certain amount of charge based on what the voltage tells you. R is the resistance. Think of that as like, well, I mean, it is what it is. It's just what it sounds like. It resists electricity flowing through it. Like friction kind of resists you pushing a desk across the floor. The greater the friction, the harder it is to make it slide. If you put it on ice, it's going to be easier to slide, like on a smooth ice skating rink, versus trying to slide it across a carpeted floor. Okay? And then I is the actual amount of charge that is moving. It's charge per unit time, so it's kind of like water flowing through a pipe. Okay? So that's what's going on here. We're going to try and push the current I, the charge I, through the resistor that has a certain amount of resistance to it, and then we have a certain amount of strength, voltage, to actually push it through there. So the idea is, that's what this is relating, is your strength to the amount of current you can push through, to the amount of how difficult it is to push the current through that resistor. All right, so V is a constant voltage and it's in volts. I is the current, it's measured in amperes, and R is the resistance, and it's measured in ohms. Okay, amperes is usually a capital A, ohms is the Greek letter capital omega, and voltage is listed in volts, and it's done with a V. V is both the unit and also the variable used for it. So your firm has been asked to supply the resistors for a circuit in which V will be 120 volts, and the current, I, has to be 10 amps plus or minus 0.4 amps, plus or minus 0.5 amps. In which interval R does R have to lie for I to be within 0.5 amps of the value of 10 amps? Okay, so basically this could be a very real world problem. You have a certain tolerance, you can be up to 10.5 amps and as low as 9.5 amps, but you have to be within there. So how precise do you have to be with your resistors? How accurately do you have to make your resistors and produce them in order to meet the requirements of your customer? All right, so let's take a look at this. First off, we have V equals 120 volts. I is going to be the 10 plus or minus 0.5 amps, like that. And we have Ohm's law that was given, V equals IR. And from that, we can say that I is V over R. And this is going to be R f of x. All right, it's I as a function basically of R here. All right, and so we can say then that I equals this 10.5 amps, which means that we also get that V over R equals 10 plus or minus 0.5 amps. Okay, now you're seeing where we've got our little uncertainty in there, which means we can have V over R minus 10 is equal to our plus or minus 0.5 amps, and this has to be in amps too, just like that. And essentially what that is our f of x. Remember we said this was f of x minus our limit factor. This is basically our L, right? That's what we have there. And so what we've got is V over R minus 10 amps, just like that, has to be less than or equal to 0.5 amps, which has to be greater than or equal to negative 0.5 amps. So there's our range that we have to be within, okay? And so we can go through and start plugging these numbers in. And so the voltage is 120 volts, right up there at the top, 120 volts over R, and then minus our 10 amps, and again the 0.5 amps and the negative 0.5 amps. And then what we can do is add the 10 amps everywhere. So this will become 9.5 amps. And this one over here will become, so this is 120 volts over R. And then this one over here will be 10.5 amps. Just like that. We can take the reciprocal of everything. In other words, we're going to multiply. We're gonna just take the reciprocal of everything, which means we have to flip our greater than or and less than signs. So this becomes 1 over 9.5 amps. And then swap our sign around. This is R over 120 volts. Flip our sign around. 1 over 10.5 amps. So think of it this way. Why we flip our signs around that? 4 is less than 7, but 1/4 is greater than 1/7, right? So when we take the reciprocals, we have to swap our signs around because a quarter of something is greater than 1/7 of something, right? I'd rather have a quarter of a pizza than 1/7 of a pizza, right? Because if this is my pizza, I want a quarter of it versus doing what, 1, 2, 3. I didn't quite get that into sevenths. I got that into sixths, but that wasn't very good. Let me try that one more time. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. So, which would you rather have? The entire quarter of a pizza or a seventh of a pizza? So obviously, a quarter of a pizza is greater. All right, just a little thing for you. So when you take the reciprocal, you gotta flip over your sign there, and then we can bring this up here because I'm running out of room down there, and we can actually then multiply everything both sides by the 120 volts. So 120 volts divided by the 9.5 amps. So this will be 120 volts divided by the 9.5 amps. And this is just R. And this is 120 volts over 10.5 amps. And so then the numbers those turn out to be is 12.6 ohms. Volts per amp is what is an ohm. And that's R, and this one turned out to be 11.4 ohms, okay? And so that's what we end up with, and then we have to find, basically just say, well, actually, they only asked us for the interval, so we just have to be within that interval. There we go. We don't have to find a single maximum value, but very similar to what we were doing with the limits, but we're basically finding the limit of what we can do when we're producing something or, picking something out. So we have to create, our resistors have to be within that value range right there in order for whoever we're supplying these to be happy and have their then machines work. Okay? That's pretty much it for that problem. Thank you.